From a satellite orbiting way up there down to the phone that's probably in your hand right now, pretty much everything that moves is governed by just a handful of incredibly powerful universal rules. We're going to see how these laws literally shape our entire world. And we're going to start with a question. And the answer might just save your life one day. It sounds completely backwards, right? I mean, you'd think safety is all about being stronger, more rigid. But in the world of physics, surviving a high-speed collision is all about some clever engineering that kind of seems to defy common sense. And the answer? Well, it's one of the most brilliant applications of motion physics you'll see every single day. That's right, crumple zones. The parts of your car that are literally designed to collapse and fold up like an accordion in an accident, those are the very things that stand between you and a catastrophic injury. So how on earth does making something weaker protect you? It all comes down to the physics of the impact itself. Okay, let's break this down. On one side, you've got a super rigid car. It hits a wall and just bounces off, coming to a stop almost instantly. That sudden, violent change in motion sends a massive, really dangerous force straight to the people inside. But a car that crumples does something amazing. It absorbs that impact energy. It extends the time of the collision, even just by fractions of a second. And that tiny bit of extra time, it makes all the difference, dramatically reducing the force that you actually feel. So this brilliant piece of safety engineering isn't just some clever trick. It's a direct application of three fundamental laws of motion. These were laid out by Isaac Newton more than 300 years ago, and they're the bedrock of what we call classical mechanics. Let's start with Newton's first rule, and it's maybe the most fundamental of all, the law of inertia. The best way to think about it is like this. It's the universe's default setting for everything. It's basically an object's built-in resistance to any change in its state of motion. And really, that's all it is. If something is sitting still, it wants to stay still. If it's moving, it wants to keep moving in a straight line at a steady speed. And to change that, to speed it up, slow it down, or change its direction, you absolutely need an outside push or a pull. You need a force. And you see this everywhere. A satellite, once you get it moving, will just glide through the near-perfect vacuum of space pretty much forever unless something else acts on it. And what about that feeling of being pressed back into your car seat when the driver hits the gas? That's your own body's inertia. Your body wants to stay put while the car is trying to yank it forward. Okay, now for the big one, the mathematical heart of it all. F equals ma. Force equals mass times acceleration. This little equation is, no exaggeration, one of the most important in all of science. It tells us exactly how much an object's motion is going to change when a force acts on it. And this brings us right back to our car crash. The second law is the why behind crumple zones. See, in any crash, your car's mass and its change in speed are pretty much fixed. But if engineers can increase the time it takes for that change to happen, even by a split second, the equation tells us the force involved has to go down. Crumple zones are literally designed to manipulate F equals ma to save your life. And finally, we've got the third law. And this one tells us that forces are never lonely. They always come in pairs. If you push on something, that something pushes back on you with the exact same amount of force, every single time. A rocket is the perfect example, right? It throws super hot gas down, that's the action, and the gas pushing back up on the rocket is the equal and opposite reaction that lifts it into space. Even something as simple as jumping works this way. Your feet push down on the earth, and the earth pushes you up into the air. So there we have it, inertia, F equals ma, and action-reaction. Three rules that sound pretty simple on their own, but from these three principles, we have engineered the entire modern world. Let's see just how big they can get. Don't just take my word for it. This quote from the California Department of Transportation's Bridge Manual, it says it all. Engineering isn't just guesswork. It's a meticulous process of using physical laws, Newton's laws, to predict exactly how a structure is going to behave under any kind of stress. I mean, look at this. Modern structural modeling gets incredibly complex. Engineers can simulate every single nut, bolt, and beam of a massive structure like a bridge. But deep inside all of that sophisticated software, at the very, very core of every single calculation, guess what you'll find? Good old F equals ma. And the applications are they're everywhere. Plotting the perfect trajectory for a probe to fly to Mars? That's Newton. Programming the precise, delicate movements of a robotic arm in a factory? Newton. Analyzing the biomechanics of an athlete's perfect golf swing? You guessed it.
His laws give us the predictive power to build our entire technological world. So, for centuries, Newton's laws seemed absolutely perfect. They worked for everything, everywhere. But as our scientific tools got more and more powerful, we started to explore realms where these elegant, perfect rules, well, they started to fray around the edges. This became one of the biggest questions in physics around the turn of the 20th century. Are these laws truly universal? Or do they have a breaking point? And the answer, as it turns out, is a definite yes. Here's the deal. In the world we actually experience, at human scales and normal speeds, Newton's laws are so accurate that for all practical purposes, they are perfect. But when you push the boundaries, when you go incredibly fast or incredibly small, the universe starts playing by a completely different set of rules. For things that are very, very fast, the new rulebook was written by Albert Einstein. His theory of special relativity showed us something mind-blowing. The speed of light is the ultimate cosmic speed limit. And as you get closer to it, reality itself starts to warp. Time actually slows down for you, and distances shrink. And this is not just a theory. At particle accelerators like this one, they can get particles up to 99.7% of the speed of light. At that velocity, the effects are huge. Time for those particles slows down by a factor of almost 13 compared to us. Newton's simple F equals ma just can't explain that. It breaks. And then if you go to the other extreme, the unbelievably tiny world of subatomic particles, things get even stranger. That's the quantum realm, where particles can be in multiple places at once and seem to teleport. In these wild, exotic domains, the classical, intuitive rules of Newton they give way to the profoundly weird and wonderful rules of modern physics. So, does that mean Newton was wrong? Not at all. Not even a little bit. It just means that as brilliant as his laws are, they have their domain of mastery. And that domain happens to be the everyday world that we live in, the world we can see and touch and build things in. You know, the incredible success of Newton's laws gave us the power to build our modern civilization. And their limitations, the places where they finally broke down, those weren't failures. They were the very clues that pointed physicists towards the deeper, richer, and honestly stranger reality of relativity and quantum mechanics. It really makes you wonder, doesn't it? The rules we use today, from Einstein to quantum mechanics, they seem to describe the universe perfectly, just as we see it now. But what happens when we push the boundaries again? What new extremes will we reach that reveal the next layer of reality? What other universal rules are still out there, just waiting for us to find them?